All right. Good morning, everyone. All right. Today, I want to start with a little bit of a review. So, given this data set of five numbers, I would like for you to find for me the mean, the median, and the standard deviation. Mhm. I'll give you guys a few minutes to get that done. Almost there. I'm just gathering some questions before we begin. Are we almost there? We almost there. Take another couple minutes, finish up that first problem, please. right, all right, all right, all right, all right. We just click this real quick. And all right, we're looking good. Okay, so I have 5 numbers here, right? I want to do 3 things. I want to get the mean, the median, and the standard deviation. So let's talk about the mean, all right? Once again, looking at our formula sheet. Sorry about that. Looking at our formula sheet, we know that the mean, all right, is equal to the sum of x divided by n, which means you want to sum the x values, divide it, and then you want to divide it by the counts of the x values. Right? I feel like everybody is good with this. Right? I'm gonna cheat a little bit because of the interest of time. So for my x, I got 15.85. I got 18.65. I got 6.48. I got 0.49. And I got 7.57. There we go. That looks really good, right? So what I want to do is I want to get the sum of the x values. So the sum of x, which remember just means I'm adding them up. That's all I'm doing, right? Equal to the sum. These numbers here. Let's see what we get. Boom. All right. So just to be clear, I'm talking about 15.85 plus 18.65 plus, I'm going to skip a few because of space, all the way down to the last number, which is 7.57. And then what I want to do, I want to divide this by the number of numbers. And how many numbers do I have? I have 5, right? That's my goal. That's my goal. Now, from the calculator, I see that my sum is 49.04. And I want to divide that by how many numbers I have there? 5, right? So let's take a look. 49.04 divided by 5, what's that? That is 9.808. And there you go. That's your mean right there. That's the mean. Little preference, I like to highlight a little bit. I'm one of those highlighting people, so now you guys know. All right, let's move on to the next one. I'm gonna change the color up for this a little bit. I'm gonna go with my orange, right? So for the next part, I want the median. Now, remember, in order to find the median, I have to put my numbers in order, right? And I like to do it from smallest to largest, right? So we're gonna look at our numbers here. I believe 0.49 is the smallest. My next number will be, I think, the 6.48. And my next number after that will be the 7.57. And my next number after that will be the 15.85. And my final number will be the 18.65. Now, after I figure that out, I want to just cross out the end terms, and then the one that's in the middle, that's my median. So what's my median? 7.57. All right. Don't mind me. I'm a highlighter. All right. I like to highlight my things, but I'm not gonna lie, I don't like that color. Let me try the green. Let me see if that pops a little bit better. Nope, don't like that either. We're going back to yellow. Okay. All right. All right. All right. There we go. There we go. There we go. There we go. Okay. All right, let's move on. Last but not least, I want to find my standard deviation. And then now to find my standard deviation, you know that I'm going to need to make a list, right? So the list that I like to make is I like to do my x's and then my x squares, all right? So let's do that list right here. I'm just copying from what I have above. So for my x's, I have 0.49. You do not need to put this list in order. I'm only copying from what's above out of convenience, okay? But you can use the original list, no problem, and you will get the same answer. I mean, the original order of the list, and you will get the same answer. All right. 7.57, 15.85, and 18.65. All right, just let me verify something real quick. This is 15.85, 18.60. Okay, perfect, 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 perfect. Okay, all right. Now that I have my list of my x's, the next thing that I want to do is I want to square each one of them, right? I want to square each one of them. So I'm literally going to do x squared, right? So let's square each one of these, right? So we're just going to raise that to the second power. Boom. There we go. And then you know you're going to do this all on your paper. Boom. And then you just get your squares right there. After you're done squaring them, what I want to do is I want to find their sum. So I want the sum of x, right? And we know the sum of x is just equal to the sum of these numbers, even though we already have the sum of x. We knew what it was from before, 49.04, right? But now we're going to have something new. We're going to have the sum of x squared, right? The sum of x squared, that's new, right? So for our sum of x squared, let's see what we're going to get. Perfect. So we have 698.5804. You guys should verify on your own or using your calculator that you got these same numbers as well. All right. And then now what do we want to do? We want to jump straight into our formula. So our variance, that's how we start off. We always start off with the variance. Our variance is equal to s squared, which is the sum of x squared minus, open parentheses, the sum of x, and then we square that divided by n, our number of numbers, and then divide that again by n minus 1. All right, very simply, let's just plug in our numbers. So what's my sum of x squared? It's 698.5804 minus, open parentheses, the 49.04 squared divided by my n, which is 5, and then all of this divided by 5 minus 1. Now, so a lot of people doing this yesterday. Right after you gave me the formula, and then you plugged in all the numbers in the correct place, I want you to then type it directly into your calculator, the same way that you have it written on the paper. It should look the same way that it looks on paper in your calculator, right? Remember your fraction button. Press the fraction button, enter in the numbers as you see fit, right? I'm going to do that right now on my own and then see what the answer is. So basically, I want a formula, plug in the numbers, and then give me the answer right then and there. That's how I like to do it. All right. So let's see. So we're going to have the sum of x squared minus parentheses. We're going to have the sum of x, and we're going to square that. And then we want to divide that by the n, which is 5, right? And then we want to then divide this by 5 minus 1, the denominator. Boom. So now, what do we have? We have 54.39902. Notice I don't round that, right? I can't round that because that is my variance. That is not my standard deviation. It's not my final answer, right? So to get my standard deviation S, right, I have to square root my variance, right? So if I square root my variance, which is 54.39902, if I square root that, what do I get? Let's see. It's QRT, right? Yeah. Now you can round off your standard deviation if you want to. As you know in class, I'm not a fan of rounding, right? So I'd rather you just give me everything. But if you want to round this off, you have my blessing. 3,755,69. All right. Generally speaking, I personally like if I'm gonna round off, like four decimal places, right? So four places after the decimal. So 3, 7, 5, and then 6. All right. Let's say that you want to go a step further, right? You want to go a step further. Let's look back at our numbers real quick. I'm going to show you guys something intelligent. All right. So all of my numbers from the beginning all went out to the 100th place, right? They all went out to the 100th place. So because of that, doing the math without the rounding and all of that, I could kind of trust the tens place a little bit, right? I could kind of trust the tens place a little bit more than I could trust like the rest of the numbers, like the hundredth and the thousandths place. Maybe even the hundredths place, I could get away with trusting that. But really the tenth place is my golden number. I could trust that that's going to be correct. So I guess if you wanted to give me 7.38, that would be okay as well. All right. But my favorite, the one that I'm gonna select, the one that I'm gonna highlight is the one that's everything. All right. Not a fan of rounding, right? Every number is significant, every number is important to me. All right. There we go. If you have any questions, all right, you can always ask them in tutoring. You can ask in class. All right. And we'll talk soon with that. It's a good question too. All right. So question 2 says, a botanist is studying the relationship between the amount of sunlight a plant receives and its growth. They record the average daily sunlight in hours and the plant's height in centimeters after 1 month for a sample of plants. And then there you go. You have your average daily sunlight in hours, and you have your plant height, which is given in centimeters, right? So I want you to do 3 things for me here, right? The first thing that I want you to do, oh, I'm sorry. Let me get my pen. Apologize for that. The first thing that I want you to do is I want you to give me a scatter diagram. The next thing that I want you to do, all right, is I want you to tell me what you think the correlation coefficient is for this question. You do not have to give me the correlation coefficient. You don't have to find it. Just tell me what you think it is. I'm only interested in the sign of it. That's all I'm interested in, right? So what is the sign of the correlation coefficient? Specifically, all I'm looking for, positive or negative. That's specifically what I'm looking for, right? And then in part C, the third thing I want you to do, just interpret your answer. That's it. All right, give you guys a minute to do that. All right, all right, all right. Let's get this done. So the first thing is I want to make a scatter diagram, right? Just like that. This is going to be my x's, my x-axis, excuse me. This is going to be my y-axis. Very simply, all right? And then, of course, in the corner right here, this is 0. Now, my x's are going to be my, trying to think real quick. Let me think. I feel like I would rather make the hours my y and make the x's my planned height. Now, as long as you are consistent, you will still get the right answer with what I'm about to do, right? So I'm going to switch my x and my y, right? As you can see in the story didn't flat out tell me what is x and what is y. So I have the leeway to choose what I'm going to call x and what I'm going to call y. I feel like calling the y, right? My hours, because the biggest number there is 7. And it's easier for me to go from 0 to 7. So I'm going to call y hours, right? So just so I'm clear, I'm calling this column y. And then I'm going to call the plant height x. So I'm going to call this height. I'm going to call that the height, which is given in centimeters, by the way. All right. It just makes it easier. Just trying to make life easy. That's all. All right. Now I have to get to 7, right? Kind of easy for me to get to 7. I'm trying to think, how do I want to do this? Do I want to do this by ones? Do I want to do this by twos? I'm going to do it by twos. All right. So 2, 4, 6, 8, and I'm done. This is why I wanted to do the hours. Because you see, my y axis is not as long as my x axis. So that's why I did that. Let's take a look at the x now. All right. I'm calling this one x, by the way. All right. So I want to go from 0 to 20, right? From 0 to 20. And I can decide however I want to do it, right? Do I want to go by twos? Do I want to go by threes, by fives, right? I feel like fives would be too much. I want to go by twos. I'm thinking. Yeah, let's go by twos. We'll go by twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right. That's just how this problem worked out, right? Now listen, because I switched my columns, right? The column that I'm calling X and the column I'm calling Y, I have to read this backwards from right to left, right? Read this backwards from right to left. So my first ordered pair, let me get a color real quick, is going to be what? It's going to be 10, 3, right? So the first ordered pair, this one is 10, comma 3. So I'm going to come across the x-axis to 10, and I'm going to go up to where 3 is, and I'm just going to make my mark. There we go. Ooh, I could do a little bit better than that. There we go. Yeah, that looks good. All right. My next point is going to be what? 15, comma 5. Right? I'm just writing them out like this so that you can see that because of the switch, right? The second column is now X and the first column is now Y, right? So I'm just writing them out clearly so that you guys can see. And I did this because of the bounds of my graph. Doing this, switching the X and the Y column does not change your answer, right? You will still get the same answer, okay? So, I didn't mean to do that. So back to what I was saying, that was 15 and 5, right? So 15 and 5. So I'm coming across to 15, going up to 5, which I believe is somewhere like here. Again, do your best. We are not machines. All right. So I'm not expecting perfect answers here. Just do your best. Where you can approximate that it's going to be. The next one is 8, 2. Right. So I'm going to come across the 8, going to go up to 2. Next one is 18, 16. Excuse me, 18 and 6. Apologize for that. 18 and 6. Let me go up. Feel like I'm starting to see the correlation yet. Are you guys starting to see the correlation? All right. So this next one is 12 and 4. Going up to 12, going up to 4. Starting to see the correlation a little bit. All right. Next one is 20 and 7. So I'm going across to 20, going up to 7 right here. And my last one is 5 and 1. I'm going to cross to where 5 is, and I believe 1 is somewhere like right here. Boom. Right? All right. So now let's look at part B. Right? So for part B, let me just show you guys the graph fully so you guys can appreciate it. Boom, that's A. All right, so for part B, what did we want to know? We wanted to know, right? What is the correlation coefficient here, the sign of it? What would you estimate the correlation coefficient to be, right? So I would estimate the correlation coefficient to be positive in this question. And why is it positive? Because I notice that if I read my graph from left to right, the same way that I read a book, that the trend is increase. All right. So I call that a positive correlation. That's for part B, right? Right. Now for part C, I just want to interpret my results, right? And what is the interpretation of my results, right? The interpretation of my result is as the, let me see if did they tell me what it is? Okay. So as the height of the plant increases, the, let me scroll back up and go back up to the story. The average amount of time in the sun increases. Right? And we remember, right? Remember our interpretation. So as x, right? So height in this case is x, increases the, let me see, time in the sun, let's call that the y, increases. All right. So as x increases, y increases. All right. That's our interpretation. Because we have a positive correlation, right? Just to recap, if it was a negative correlation, right? If our correlation was decreasing from left to right, like so, say our correlation was decreasing from left to right, like so, right? Then our interpretation would be as the x is increasing, the y is decreasing. Okay. And that's that. Again, if you have any questions about this or you'd like to elaborate on a little bit more, please come through to tutoring. Again, tutoring will be both in person and online today, right? 12 to 6. All right. Next time after today, tutoring will be open again on Monday. All right. Please practice this at home. All right. I'll give you guys a couple minutes to do these next two. You know what? Let me just bring this up a little bit. I realize that you can't see the whole question. There we go. All right. So there's a part A and a part B to this question. It's part A. Ooh, that's not good. I'm gonna try that a little bit smaller. There we go. That's part A. That's part B. Okay. So a nursery sells rose bushes. 60% of the rose bushes are red, and of all the rose bushes, 80% live their first year. Of the red rose bushes, 90% survive their first year. What is the probability that a randomly selected rose bush will be red and survive its first year? Boom, that's your first question. Next question. In a large office building, a study found that 12% of employees had experienced the flu during the past year. 8% had experienced a cold, and 3% had experienced both the flu and a cold. What is the probability that a randomly selected employee has experienced either the flu or a cold in the past year? Go ahead, do that question real quick. Give you guys a couple of minutes. And I think that should be enough time to get these questions done. So a nursery sells rose bushes. All right, in honor of the rose bushes, we'll keep the same font color. Okay, anyway. A nursery sells rose bushes. 60% of the rose bushes are red. Of all the rose bushes, 80% live their first year. And of the red rose bushes, 90% survive their first year. What is the probability that a randomly selected rose bush, right, will be red and survive its first year? All right. So we want to know. Hold on 1 second. So we want to know what is the probability of red and I'm going to say first. It really is survive, but I'm just going to say first. It's an easier word, right? So this is what they're asking me to do, right? Let's look at what I have, right? So I have the probability of red, which is 60%. I have the probability of first given rose, that's 80%. And then I have the probability of, first given red. That's 90%. Okay. So we want to match them, right? You remember that your formula is the probability of A and B is equal to the probability of A, the probability of B given A times your probability of A. Again, this is on your formula sheet. We're looking at chapter 5, where you can find that formula, right? Once again, just want to highlight this. Remember, whatever comes after the given is the one that stands alone over here, right? So the only standalone part that I have in this question is the probability of red. But which one of these given statements has red after the word given? Only the second one, right? So this is going to be times the probability of first given red. After that, just do the math, right? What's that going to be? 60% times 90%? Little calculator, right? I'm going to do that real quick. So I got 0.6 times 0.9. Let's take a look at what that is. Make sure that that's right. Awesome. So I got 0.54. And that's it. And you know I like to highlight. And that's it for the first question. Not too bad, right? So break it down into what they're giving you, plug it in, and that's the end of the question. All right. Let's take a look at B. A large office in a large office building, a study found that 12% of employees had experienced the flu during the past year. 8% had experienced a cold, and 3% had experienced both the flu and a cold. That sucks. What is the probability that a randomly selected employee has experienced either the flu or a cold in the past year? All right. So let's take a look. right? My keyword here is or. As soon as you hear or, you write down your or formula, right? So this becomes what? Probability of A or B is equal to probability of A plus probability of B minus probability of A and B. I'm not making this up. I'm just copying this directly from the formula sheet. This is in chapter 5, general addition rule, right? Right after you get that, just plug in the story. Keep it simple, right? This is going to be the probability of flu or cold. And that's going to be what? The probability of the flu plus the probability of a cold minus the probability of both. And that's it. After that, just give them the numbers, right? How many people had the flu? I think it was what? 12%? How many people had a cold? 8%? How many people had both? 3%. All right. After that, just do a little bit of math, right? This is going to be what? 20 minus 3, let's call that 17%. And then that's it. If you also want to give me 0.17, I'll take that answer as well. All right. Any one of these answers is good. All right. Again, you know, I like to highlight. I'm a highlighter. That's my thing. That's my jam. All right. Awesome. Awesome. All right. Let's take a look at question 4. Something we did yesterday. It says a coin is biased. Oh, shoot. This is that Fordham University. Ooh, this is that Fordham Road question right here. A coin is biased such that the probability of getting heads is 0.6. If the coin is flipped 7 times, what is the probability of getting more than 4 heads? All right. So let me just write this out real quick. They want to know what's the probability of more than 4. All right, I'm gonna let y'all do that. After you guys finish that, the next thing I want to know, right? I want to know what is the expected value. What is the expected value of this question? And after that, I want to know what is the standard deviation of this question. Give me the standard deviation of this question, all right? Give you guys about 2 minutes or so to do this. Remember, you can either use the calculator or you can use the formula sheet, your choice, all right? All right, good. So let's take a look at this, right? They want to know, right, the probability of more than 4. Let's take a look at what we have. What was I given in the question, right? So I was given that the coin is being flipped 7 times, right? I'm given that the coin is biased, right? And the probability of getting a head is 0.6, right? And then they want to know what is more than 4 heads. right? So just to be sure, right? My n, which is my sample size, is 7. My probability of success in this case is 0.6. And I want to know what is the probability of more than 4. Hold on, I have to think for a second. What numbers are more than 4? Right? More than 4. So that must mean that they want to know what is the probability of R, or you can say X, greater than 4. So what numbers are greater than 4? That must be the numbers like 5, like 6, and like 7. Okay, now this is starting to make a little bit more sense now, right? So I want to know what's the probability of 5, 6, and 7. Now, again, you get it off of the formula sheet if you want, or you can use the calculator. I'm going to do it the calculator way, right? Remember that our calculator cannot, right? Let me say it again. Our calculator cannot, right, give us probabilities for greater than. It can only give us probabilities for less than, right? To be clear, calculator can only give us probabilities for less than or equal to, less than and equal to. That's what it is, less than and equal to, right? That being said, what can I do in the calculator? I can do the complement of this. I can do 1 minus the probability of R less than or equal to, right? What number? 4, right? Because remember, 4 is not included in this, right? So I'm going to calculate on the calculator the probability of 4, 3, 2, 1, and 0. And I'm going to subtract that from 1, because remember that all probability has to add up to 1. So if I take the whole of 1 and subtract out the part that I don't want, I'm left with the part that I do want. All right. So very simply in your calculator, this should be 1 minus the binomial CDF, where your trials is your N, which in this case is 7. Your probability of success is your P, which is 0.6. And your X, or your R value, that should be 4. All right. Input it in the calculator, boom, 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 and it should give you the answer. I'm going to get the answer right here. And then I'm going to highlight it for you. Just going to do it right here real quick. All right, so you should all get in your calculator this answer 0.419904, right? You should get an answer that is similar to that if you're doing it off of the formula sheet. No problem. Either way works. And that's our answer for A. All right, let's look at the second question. The second question is asking me for the expected value, all right? I'm gonna switch this up. All right. So the second question is asking us for the expected value. Expected value is also known as mu, right? So our formula on our formula sheet is mu is equal to N times P. Very simple, very simple. And what is my N? My N was 7, right? And what is my probability of success? 0.6. So all you're doing is 7 times 0.6. And then what do you get? I think it's 4.2, but don't quote me on that. Let me check. This is going to be 7 times 0.6. Boom, 4.2. Oh, shoot. Feeling lucky today. Feeling lucky today. All right, and then that's it. Let me get a little highlighter real quick, because you know I like to highlight, right? You know I like to highlight. There we go. Boom. All right, that's it. Last but not least, let me get a nice color. Let me get a nice color. Oh, yeah. All right. They're asking us for the standard deviation, or sigma. All right. So now on our formula sheet, sigma is equal to what? The square root of n times p times O parentheses 1 minus p. Very simple, very simple. Just plug it in. Don't overthink it, right? This is going to be 7 times 0.6 times 1 minus 0.6. Plug it in your calculator, boom, 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 and then you get the answer. Very simple, very simple. So this is going to be equal to the square root of 7 times 0.6 times, open parentheses, 1 minus 0.6, close parentheses, boom. All right, so final answer, I got 1.296148. You know, I don't like to round. If you're going to round, give me 4 decimal places, make me happy. And that's that. All right, all right, all right. Now let's move on to our lesson for today. All right. So today, yeah. So today we're gonna be doing, it's our 4th day, something called normal distributions. Yippee. All right. So a couple things we're gonna want to talk about. This shouldn't be too bad. All right. This is another question that you're going to get on the final. So we're going to be talking about standard units and areas under the standard normal distribution. All right. So z-scores and raw scores. All right. Normal distributions vary from one another in 2 ways. The mean mu may be located anywhere on the x-axis, and the bell shape may be more or less spread according to the size of the standard deviation. The differences among the normal distributions cause difficulties when we try to compute the area under the curve in a specified interval of x values, and hence the probability that a measurement will fall into an interval. Okay? This is going to get real simple real fast. Don't worry. So it would be futile. It would be a futile task, excuse me, to try to set up a table of areas under the normal curve for each different mu and sigma combination. We need a way to standardize the distributions so that we can use one table of areas for all normal distributions. We achieve this standardization by considering how many standard deviations a measurement lies from the mean. In this way, we can compare a value of one normal distribution with a value in another different normal distribution. The next situation shows how this is done. Oh, this is awesome right here. Awesome, awesome, awesome. Okay. So suppose Tina and Jack are in 2 different sections of the same course. Each section is quite large, and the scores on the midterm exams of each section follows a normal distribution. In Tina's section, the average mean was 64 and her score was 74. In Jack's section, the mean was 72 and his score was 82. Both Tina and Jack were pleased that their scores were each 10 points above the average for each respective section. However, the fact that each was 10 points above the average does not tell us how each did with respect to the other students in the section. All right. So in the next figure, we will see that the normal distribution for grades of each section. Oh, let me show y'all. It's gonna be good. No, don't tell me you froze too. Oh, Jesus. Mm. Seemed like everything freezing today. Yeah. Computer freezing. You freezing. Oh, Lord. What just happened? Hold on a second. Bear with me 1 second. Like I'm having a little technical difficulties over here. Into my mouse just now. It's like everything just froze on me. Sorry about that, y'all. Just get this back up. See how everything's going. No. But bear with me 1 second. Hold on. Let's see, that's good. I think we're back. I apologize about that. I know the suspense is killing everybody. Sorry about that. I'll blame the weather. To be honest, I'll blame the weather. I do. All right. So Tina's 74 was higher than most of the other scores in her section, while Jack's 82 is only an upper middle score of his section. Tina's score is far better with respect to her class than Jack's score is with respect to his class. Let me show you guys why. Let me show you guys why. So as you can see right here, right? This is figure 711 real quick, right? The first graph, this is Jack's section, right? Yeah, Jack got an 82, 10 points above the mean, right? But as you can see, right, it's everybody's score is just so spread out that it's not as impressive as Tina's score, right? Because you see Tina, she got 10 points above the mean, but the class is just so narrow, you know? It's like she's in like the top percentile of her class, you know, whereas Jack is like he's up there, but he not in the top percentile of his class, you know? That's the difference. So the preceding situation demonstrates that it is not sufficient to know the difference between the measurement x value and the mean of a distribution. We need also to consider the spread of the curve or the standard deviation. What we really want to know is the number of standard deviations between a measurement and the mean. This distance takes both the mean mu and the standard deviation sigma into account, right? That's what we're looking for. Mhm. So we can use a simple formula to compute the number z of standard deviations between a measurement x and the mean mu of a normal distribution with standard deviation sigma. So the number of standard deviations between the measurement and the mean is equal to the difference between the measurement and the mean divided by the standard deviation, right? Now I know that that kind of sounds a little crazy, so let me put some mathematical symbols in there, and that might make it pop to you a little bit. So the Z value or Z score, also known as the standard score, gives the number of standard deviations between the original measurement X and the mean mu of the X distribution. So Z is equal to X minus mu over sigma, right? This is on our formula sheet. This is actually in chapter 7, right? So if you look at chapter 7 on your formula sheet, you'll see this formula right here, all right? So let's talk about our standard score. So the mean of the original distribution is always 0 in standard units. This makes sense because the mean is 0 standard variations, excuse me, from itself. An X value in the original distribution that is above the mean mu has a corresponding Z value that is positive. Again, this makes sense because a measurement above the mean would be a positive number of standard deviations from the mean. Likewise, an X value below the mean has a negative Z value. All right. Good stuff, good stuff, good stuff. I just want to make this pop a little bit more. This is what is going to make up our question. So we have X values and corresponding Z values. X is the value in the original distribution, the story, right? Where X could be equal to the mean, X could be greater than the mean, or X could be less than the mean. The corresponding Z value or standard unit would be Z is equal to 0, or Z is greater than 0, or Z is less than 0. All right. All right, so let's talk. All right. What does a standard score tell us? So a standard score or a Z-score of a measurement tells us the number of standard deviation the measurement is from the mean. A standard score close to 0 tells us the measurement is near the mean of the distribution. A positive standard score, Z value, tells us that the measurement is above the mean, and a negative standard score tells us the measurement is below the mean, right? That's it. All right, let's keep going. So I want to talk about the standard normal distribution, right? So if the original distribution of X values is normal, then the corresponding Z values have a normal distribution as well. The Z distribution has a mean of 0 and a standard deviation of 1. The normal curve with these properties has a special name, right? So we're going to look at that. So this is the standard normal distribution, and it is a normal distribution with mean mu equals 0 and standard deviation sigma is equal to 1. Okay. So any normal distribution of X values can be converted into a standard normal distribution by converting all the X values to their corresponding Z values. The resulting standard distribution, right, will always have a mean mu is equal to 0 and a standard deviation sigma is equal to 1. All right. So that's what we're getting at. Let's talk a little bit about this. So what does a standard normal distribution tell us? When we have a standard normal distribution, we know that the mean is 0, the standard deviation is 1, and any normal distribution can be converted to a standard normal distribution by converting all the measurements to standard Z scores. All right. All right, let's take it up a notch. I want to talk about areas under the standard normal curve. All right. So we have seen how to convert any normal distribution to a standard normal distribution. We can change any X value to a Z value, easy, and back again. But what is the advantage of all this work? The advantage is that there is an extensive table that shows the area under the standard normal curve for almost any interval along the Z-axis. The areas are important because each area is equal to the probability that the measurement of an item selected at random falls in this interval. Thus, the standard normal distribution can be a tremendously helpful tool. So for those of you that want to use the table, this next section is for you. But when we get to our questions, it's going to be quite simple. A lot more simple than this. So using a standard normal distribution table, right? Using a table to find areas and probabilities associated with the standard normal distribution is a fairly straightforward activity. However, it is important to first observe the range of Z values for which areas are given. The range is usually depicted in the picture that accompanies the table. So in this text, we will use the left tail style table. This style table gives cumulative areas to the left of a specified Z. Determining other areas under the curve utilizes the fact that the area under the entire curve is 1. Taking advantage of the symmetry of the normal distribution is also useful. The procedures you learn from using the left tail style normal distribution table apply directly to cumulative normal distributions, the distribution areas found on calculators and in computer-aided software such as Excel, Minitab, and SPSS. All right, so that's just giving you guys a little bit of a heads up of where this is going to. So here we go. Standard normal distribution table. So we want to use the table 3 in the appendix to find the described area under the normal curve, right? The area under the standard normal curve is to the left of Z equals -1. All right. So I'm going to show you guys real quick. This is the question. What is the probability of Z less than or equal to -1, right? So the area to the left of Z is equal to -1, right? You first shade the area to be found on the standard normal distribution curve as shown. Notice that the Z value we're using is negative. This means that we look at the portion of table 3 of the appendix for which the Z values are negative. in the upper left corner of the table, we see that the later Z, the column under Z gives us the unit's areas and tenths value of Z. The other column headings indicate the hundredth value of Z. Table entries give areas under the standard normal curve to the left of the listed Z values. To find the area to the left of Z is equal to -1, we use the row headed by -1 and then move to the column headed by the hundredth position, 0.00. This entry is shaded in the table, and we'll see the area is 0.1587. So let me show you what we're talking about. So if I was gonna look it up in the table, this is your normal distribution table, right? I want -1.0, so on the Z, I come down to where it says -1 and then I go to where the 0.0 is, and I look at where do they intersect that, right? Where do they intersect that? So they both intersect. Yep, that's the normal distribution table. It's the second to last one. Mm-hmm. So wherever they intersect that, in this case, it's 0.1587, that's your probability. Right? So that is how to use the table. Let's say I ask you to find the probability of Z less than 1.18, positive 1.18. Would you do that? So you want to go to the positive Z table, right? Where the positive Z's are, these are negative. And you want to go to 1.18. So 1.1, and then go across to the 8. What number do you get? Mm-hmm. And then go across to the 8. So remember, I'm looking for like, where do they intersect that? Where do they intersect that? So 0.1190. 0.1190. All right, let's check it. Not quite, not 1190. So just to show you, this is the graph that I'm looking for. Right, I want the area to the left of Z equals 1.18, right? So more specifically, the table that I want, right? I'll let you try it before I jump into it. That sounds better. That sounds better. Well, you found it. So here you go. So I go to the positive Z table, right? And I look for 1.1. I go across the top and I look for 0.8, and they both intersect at 0.8810. That was beautiful. That was beautiful. And that's the answer to my probability. All right. That's to find a probability of the Z-score less than something. Yeah. So in this case, we're looking for an area to the left of a positive Z value. So we look in the portion of table 3 that shows positive Z values. Again, we first sketch the area to be found on a standard normal curve as shown. Look in the row headed by 1.1 and move to the column headed by 0.08. the desired area is shaded, right? So we see that the area to the left of 1.18 is 0.8810. Give you guys a little procedure real quick. So how to use a left tail style standard normal distribution table. For areas to the left of a specified z value, we use the table entry directly. For areas to the right of the specified z value, meaning that I'm asking what is the probability of z greater than a number, you look up the entry for a z and subtract that area from 1, right? So our z tables can only give us the probability of z less than a number. It cannot give us the probability of z greater than a number. So if the question asks us for a probability of z greater than a number, we have to do 1 minus the probability of z less than a number, right? And then for areas between two z values, z1 and z2, where z2 is greater than z1, you subtract the area table from for z1 from the table area for z2. What that means is that if I ask you for a probability that's in between two numbers, you're gonna take the probability of the big number and subtract that from the probability of the little number, right? Your test won't have that, but this was something that was covered, right? What I really need you to know is numbers 1 and 2. If the area is to the left, you copy it from the chart, that's it. If the area is to the right, then you have to do 1 minus that area, all right? Again, this is for all those who don't have the calculator. On the calculator, we're going to do something a little bit different. All right. I just want to kind of put a picture to all of this real quick before I move on. So let's say that the area is to the left of the z value, in other words, the probability of z less than a number, right? This is how the graph would look. Let's say that I ask you a question where we want to know what's the probability of z greater than a number, right? Well, to find z greater than a number, you're going to have to take the entire area, everything, right? This is the 1, right? When we say that it's a 1, this is the 1 right here. We're going to take the entire area and subtract the part that we can find in the table. And that's going to give us the answer to the question that we're looking for. All right? That's it. I want to make a little comment. I don't believe that this will happen on the final, but you guys should know this. So I'm just going to make a little bit of a comment if you're using the table. So the smallest z value shown in the table is negative 3.49, while the largest z value is positive 3.49. These values are respectively far to the left and far to the right on the standard normal distribution, with very little area beyond either value, right? We will follow, right, the common convention of treating any area to the left of z value smaller than negative 3.49 as 0, just flat out 0. And similarly, we will consider any area to the right of the z value greater than 3.49 as 0 as well. So we understand that there is some area in these extreme tails. However, these areas are each less than 0.0002, right? So now let's get real about this, right? Some have very specialized, one second. applications beyond the scope of the book, right? Do we need to measure areas and corresponding probabilities in these extreme tails, right? But in most practical applications, we follow the convention of treating the areas in the extreme tails as zero. All right. Just to sum up what I'm saying, right? So treat any area to the left of the z-value smaller than negative 3.49 as zero, and treat any area to the left of the z-value greater than positive 3.49 as one. All right. This special note is actually on the formula sheet. It's written very, very, very small at the bottom of each side, right? So you can see that there. I don't believe that you will run into this issue on the final, but in case, you guys know now. All right. Now let's get to what I really, 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 really want to talk about. I want to talk about the area under any normal curve. All right. This is now your real question that you're going to be asked. The area under any normal curve. All right. So normal distribution areas, in many applied situations, the original normal curve is not the standard normal curve. Generally, there will be a table of areas available for the original normal curve. This does not mean that we cannot find the probabilities that a measurement X will fall into an interval from A to B. What we must do is convert the original measurement of X, right, to A and B to Z values, all right? So that's what we do. So we're going to be given a story, and we're going to convert the story using the Z table, and then we're going to get our answers right after that. But I'm going to make this real simple when we get to the calculator, all right? Procedure. All right, so how to work with normal distributions to find areas and probabilities for a random variable X that follows a normal distribution with mean mu and standard deviation sigma. Convert the X values to Z values using the formula. Z is equal to X minus mu over sigma, and then use a table to find the corresponding probability. That's how we've been doing this. All right. Let's look at this example real quick. Let's say for a normal distribution probability, let X have a normal distribution with mean mu is equal to 10 and sigma is equal to 2. Find the probability that an X value selected at random from this distribution is between 11 and 14, right? So essentially what I'm asking you for is what is the probability of 11 less than or equal to X less than or equal to 10 with a mean of 10 and a standard deviation of 2? Always, 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 when you get your questions, you want to draw your distribution, right? Draw out your distribution. So there we go. This is our distribution right here. I want to know what is the probability from 11 to 14. I want to know about that shaded area. That's what I'm looking for. All right. So since probabilities corresponding to the areas under the distribution curve, we want to find the area under the X curve above the interval of X equals 11 and 2 or up to X equals 14. To do so, we will convert the x values to standard z values and then use the table 3 of the appendix to find the corresponding area under the standard curve. Okay. So we're going to start with our formula. And then we're just going to plug it in. Keep it simple, nothing complicated here, right? So our formula is z is equal to x minus mu over sigma. To convert the given x value to a z value, we have z1 is equal to 11 minus 10, which is our mean, divided by 2. We get 0.5. And then for z2, right, we have our x as 14. Our mean is 10, and our standard deviation is 2. Plug it in the formula, boom, 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 and we get 2.0. So now I know that instead of saying from 11 to 14 is what I'm looking for, I really only want the standard normal curve from z equals 0.5 to z equals 2. That's really all I'm looking for, right? After that, we could look it up in the table, real nice and simple, right? Let me give you a little bit of a graph just to show you what I'm talking about. 0.5 to 2. This is what we're looking for. And the work that I want to see done when you do this question is this. So they're asking you for the probability of 11 less than or equal to 14, which we're then going to change into the probability of 0.5 less than or equal to z less than or equal to 2, right? And then remember, whenever you're doing these probabilities, you take the big one, right? So this is probability of z less than or equal to 2, and you subtract it from the little one, right? Probability of z, or minus it from probability of z less than or equal to 0.5. You look these up in the chart, which you already knew how to do, and then we just subtract them, and that's the end of the question. That's it. All right. And then for us, we're going to be doing that in the calculator. One second. So I'm going to show you guys how to do this in the calculator. First, we're going to start off with our calculator. Here we go. I'm sorry, one second. I'm just trying to resize this. Okay, awesome. So just to recap, right? Let me get my pen out. We want to know what's the probability of 11 less than or equal to x less than or equal to 14, where my mean mu is equal to 10 and my standard deviation sigma is equal to, I believe, 2. Let me check. 2, right? So look, this is how you do it in the calculator, right? The first thing you're going to do, you're going to go to second, right? And then you're going to go to distribution, right? So second, and then we're going to go to distribution. And then you're going to go across the distribution, of course. And then I want you to go down to where it says normal CDF. And then I forget what comes first. I believe they're going to ask you for your mean and your standard deviation first. Am I correct? All right. So your mean does it say mean? What does it say? So mean mu is what it's saying. And then it's going to say that it's equal to 0, right? For us, we're going to change that. Because for our question, our mean is what? 10. Then they're going to ask you for your standard deviation. And for us, that's sigma. That's equals to what? 2. Then they're going to ask you for something called your lower bound, and they're going to ask you for your upper bound. Let me explain what that is real quick. All right. Always, for every question that you get that's a normal distribution, I need you to draw your distribution. Like so. We know that our mean is what? 10. And we know that they're asking us for what? 11 to 14. That's 11. That's 14. We know that they're asking us for this area right here in the middle, right? So my lower bound, hold on, let me go back. I just want you to imagine for a second before I even talk about the lower bound. Imagine that you're standing here, right? The lower bound is always whatever's to your left. And what number is to the left of me? Tell me. Not 10. Like I'm inside of the shaded area. What's to the left of me? 11, right? 11. So that's my lower bound. And what's my upper bound? My upper bound is always whatever is to my right. So what's to my right over here? 14. That's excellent. That's excellent. Right? So answer, tell me what you get. Give me the answer. Seven, 8, 7, 4, 7, right? Awesome. And as you can see, 2857, 2857, same answer. So this is how you do it in the calculator. All right. So for the final, what I want to see, I want to see this work up here, right? So I want to see first the question, like we have here with the mean and the standard deviation, right? Then I want to see this part. And I also want to see this graph. You must show me this graph. And then you can give me the answer. All right, we're gonna do more practice on this, don't worry, right? We have to talk about whenever it's less than or greater than, right? So let's do that. Let's say that I wanted the area just to the left of 11, right? So I'm asking you, what is the probability of X less than 11, right? First things first, you're gonna draw it out. Oh, I forgot also, wait. Mu is 10, standard deviation is 2, right? So first thing you want to do is you want to draw it out. So give me a distribution. I know that my mean is 10. And I'm over here at 11. And then this is the area that I'm looking for. The area to the left, right? So let's pretend for a second that I'm standing right here. Right? In my calculator, what am I going to do? I'm going to do normal CDF, where my mean is 10 and my standard deviation is 2, but my lower bound is what? This right here is called negative infinity. In your calculator, negative infinity is written as -1 E99. So that was already written there before. All right, so you're just going to do -1 E99. And then now my area extends all the way out to where? To 11. So my upper bound is 11. Then after that, you just click enter and just give me the answer. Let's see. Hold on, 0.6914. Keep going. 624 what? 68. That's it. That's all I'm looking for. That's if the probability is less than, right? This example here, this is for probability less than. Let's do the reverse now. Let's say that I want the probability of it greater than, right? So let's say I want probability of X greater than 14. I'm just making these up, right? Mu is equal to 10. Standard deviation sigma is equal to 2. All right? What are we going to do with that? We're going to first draw our distribution. So I know that my mean is 10. I know that I want up to 14. And I want the area to the right of it. I want greater than. Just like that, right? Let's pretend I'm standing right here, right? So my area to my left, or I'm sorry, we're going to do normal CDF again in the calculator, where my mean is 10. My standard deviation sigma is equal to 2. My lower bounds and my upper bound, that's what I'm trying to figure out right now. So my lower bound is whatever is to my left, right? You see where I'm standing, right? So to my left is 14. Not bad. But to my right, this is positive infinity, which in your calculator is going to be written as 1e99, positive 1e99. It should already be in your calculator, 1e99. After that, just click enter. It's 0.02275. Wait, 0.0, 75. Perfect. Couldn't ask for anything better. And that's how you do the normal distribution in the table. All right? Right. This one is for the right. This is for greater than. So we use the one formula for all three situations, when it's in between, when it's less than, or when it's greater than. I don't know about y'all, but I like this a lot more than I like using that table. You know? My opinion. All right, we got one more thing that we got to talk about, which is going to be on the test as well. And then after that, we're good to go. Uh-huh. Yeah, it could be. It could be a negative or a positive upper bound. The point is that when it's less than, the lower bound is negative. It's negative 1e99. All right, let's keep moving real quick. I have only a little bit left, and then we can call it a day at that. So the X distribution. So given that X is normal, right? In the last section, we began our study with the distribution of X bar values, right? Where X bar was the sample mean length of 5 fish caught by children and whatever, right? Let's consider this example again in light of an important theorem of mathematical statistics. So now I'm about to show you guys something. I'm about to change up the formula a little bit. So for a normal probability distribution, let X be a random variable with a normal distribution whose mean is mu and whose standard deviation is sigma. Let X bar be the sample mean corresponding to random samples of size n taken from the X distribution. Then the following are true. The X bar distribution is a normal distribution. The mean of the X bar distribution is mu, and the standard deviation of the X bar distribution is sigma divided by the square root of n. All right. So we conclude from the theorem that X has a normal distribution, right? The X bar distribution will be normal for any sample size n. Furthermore, we can convert the X bar distribution to the standard normal Z distribution using the following formula. Oh, that's about to be dope right now. Right. So we're looking at chapter 7, right? Chapter 7 on the formula sheet. That's where this formula is right here. So our mean for X bar is going to be mu X bar is equal to mu. Our standard deviation for X bar is going to be equal to the standard deviation divided by the square root of n. And then our Z value will be Z is equal to X bar minus sigma X bar minus mu for the X bar distribution divided by sigma, right? Our standard deviation for the X bar distribution. Or you can simply just say that it's going to be X bar minus mu over sigma over the square root of n, where n is the sample size. So mu is the mean of the X bar distribution, and sigma is the standard deviation of the X bar distribution. All of this is in chapter 7. You don't need to worry. All right. This formula is for those who want to use the table. This is the formula that you use whenever you're given a sample size. So theorem 7.1 is a wonderful formula. It states that the X bar distribution will be normal provided that the X distribution is normal. The sample size n could be 2, 3, 4, or any other fixed sample size we wish. Furthermore, the mean of the X bar distribution is mu, same as the X bar distribution, but the standard deviation is sigma over the square root of n, which is, of course, smaller than sigma. All right. Let's look at the difference real quick. So probability regarding X and the X bar distribution. Suppose a team of biologists have been studying the Pinedale Children's Fishing Pond. Let X represent the length of a single trout taken at random from the pond. This group of biologists has determined that X has a normal distribution with mean mu is equal to 10.2 and standard deviation sigma is equal to 1.4 in inches. So let's look at question A. So question A asked, what is the probability that a single trout taken at random from the pond is between 8 and 12 inches long? So we already know how to do this, right? This is not bad. If you can use the calculator, normal CDF, plug it in, bop, bop, and then that's it, right? If you're doing it by the table, And this is the work that you will need, right? We use the methods of 7.3, where mu is 10.2, sigma is 1.4. You have your z is equal to x minus mu over sigma, right? In this case, we have two x's because we want to know what's the probability that the trout will be between 8 and 12 inches long, right? So we're going to do 8 minus the 10.2 over 1.4, less than z, less than 12 minus the 10.2 over 1.4, which will give us a z-score of negative 1.57, less than z, less than 1.29. You look them up, subtract the two answers, bam, bam, that's it. If you're doing it in the calculator, normal CDF, lower bound is 8, upper bound is 12, enter, and then that's it, right? Let's look at question B, though. That's what I really want to get into. All right? We know how to do this part already. I want to look at question B. So check this out. What is the probability that the mean length X bar of the 5 trout taken at random is between 8 and 12 inches long, right? Okay, so now all of a sudden I have a sample size, right? All of a sudden I have a sample size N, right? So let's look at how to do this by the paper first, and then we'll talk about the calculator. Just not that bad. So bam, right? If we let mu x bar represent the mean of the distribution, then the theorem 7.1 tells us that the mean for x bar is equal to mu, which is equal to 10.2. If the standard deviation for x bar represents the standard deviation for the x bar distribution, then theorem 7.1 tells us that sigma x bar is equal to sigma divided by the square root of n, or 1.4 divided by the square root of 5, which is similar to 0.63, right? Next, we want to create our standard z variable from the x bar distribution. We subtract the mu x bar and divide by the sigma x bar to give us our formula: x bar minus mu sigma minus the mu for the x bar distribution divided by the standard deviation for the x bar distribution, which is equal to x minus mu over sigma over the square root of n. Little calculator, boom, boom. I'll give you the answer for that. This is what should happen. All right, so to standardize the interval 8 less than or equal to x less than 12, you've seen 8 less than x bar less than 12. We use 8 and then 12 in place of the x bar in the preceding formula. So 8 less than x bar less than 12 becomes 8 minus 10.2 over 0.63 less than z less than 12 minus 10.2 over 0.63. Remember, the 0.63 is the sigma divided by the square root of n. It's not the original sigma given to us in the question, right? We have to change the sigma, right? That's going to give us negative 3.49 less than z less than 2.86. After that, you're just going to look it up in the table, subtract the big probability from the little probability, and it gives us our answer. The probability is about 0.997 that the mean length is based on the sample size of 5 will be between 8 and 12 inches. Okay, so now let's talk about how to do this in the calculator. Bear with me 1 second. All right, here we go. Just bear with me 1 second. Okay. So this question, they want to know hold on. In this question, they want to know what's the probability of x less than x bar, excuse me, of 8 less than x bar less than 12, right? Where our mean mu is equal to 10.2. Our standard deviation is equal to 1.4, and our n is equal to 5, right? That's what was given to us, right? So to do this type of problem in the calculator is going to change just a little bit, right? So watch this change, right? I need what's called my mu for x bar, which is the same as the mu that I was given, which is 10.2. I need my standard deviation for x bar, which is equal to the standard deviation divided by the square root of n. In this case, this is the 1.4 divided by the square root of 5, right? You can do that in the calculator. Tell me what you get when you do it in the calculator. Yeah, 1.4 divided by the square root of 5. Square root of 5. Second square root and then 5. We have 4 decimal places. So 0.6260. All right, let's go with that. All right. So now, what I want to do, I want to draw my distribution. You know that my mean is 10.2. I know that they're looking for 8 to 12. And I want this area in the middle right here. Right? Let's pretend that I'm standing in the middle. Right here. In your calculator, you're going to do normal CDF. But here's what's going to change. They're asking you for your mean, mu, right? That's still 10.2. But my standard deviation is not the 1.4. It's what we just found in the calculator. It's the 0.6260. Then you do your lower bounds, which in this case, my lower bound is 8. And then you do your upper bounds, which in this case, my upper bound is 12. And to enter, tell me what you get. 99.77 what? Perfect. Right? Same answer that we got using the table. All right? And that's it. That's how you do normal distribution on your test. All right? This makes sense? Yeah. All right. So I'm gonna end this a little bit early because it is freezing. You know? So I want you to practice over the weekend. All right. Look back at the videos, try the problems yourself, pause them when the problem is written, try it and click play and try to see if you can do it yourself. And then we'll pick this back up on Monday. All right. Have a great weekend. Be safe. All right. Rest in peace to President Carter today. You know, Den of Thieves Part 2 comes out on Saturday. I can't wait to see that myself. All right, I'll see you guys soon. I'm also tutoring open today from 12 to 6. All right, everybody here is welcome. You can do it either in person or online, right? Just go to WC, make your appointments, and then that's it. All right. Have a good night, everyone.